Alright, in the previous section we learned the first derivative test. Now let's learn the second derivative test. And I think most people like the second derivative test more because the second derivative test is a little easier than the first derivative test. In the first derivative test we had to check if it was falling and then increasing or increasing and then falling, and that takes a lot of work. The second derivative test is easier. Here's how it works. To recap, if the first derivative is bigger than 0, then that means we're increasing. If the first derivative is less than 0, that means we're decreasing. And if the first derivative is equal to 0, then that means we're constant. So that, plus the checking, was the first derivative test. Here's what the second derivative test says. Second derivative test says that if I have a function if the second derivative is positive, that means we're concave up. If the second derivative is negative, that means we're concave down. And if the second derivative is equal to 0, then that means we have an inflection point. Okay, so what does that mean? This is important to understand. If we are concave up, then that means we are accelerating in the up direction. Concave up looks like this. At any moment in time, this particle is being pulled in the up direction. So notice that we can be falling and still be concave up, because as long as the particle is getting pulled upwards, either it's getting pulled upwards like this, or the amount it's decreasing, that rate itself is decreasing, then that means we're getting pulled up, and that's an example of concave up. Let's look at concave down. Think of concave down as gravity. The entire time our ball is being pulled towards the ground. Yeah, it's going up at first, but notice that it's going up slower and slower and slower until finally we hit a relative maximum, and then finally we're being pulled down. So concave down is like gravity in that the ball is being pulled down at every single moment in time. When is an inflection point? Let me show you. Look at this example. We're being pulled down, pulled down, pulled down by gravity, but then as soon as we hit this point right here, notice how this part of the graph is concave down. This part of the graph is concave up. This point right here would be called an inflection point, and that's when the second derivative would be 0. So when you go from concave down to concave up, that would be an inflection point. Another example of an inflection point would be this. Can you spot the inflection point? Notice here we're going from concave down to concave up. The inflection point would be right here. We're accelerating upwards, but then starting right here, we switch to concave down and accelerating downwards. So an inflection point is a point that separates being concave up from concave down. One other thing about the second derivative test, we know from the previous first derivative test that whenever the first derivative test is equal to 0, then that means we have a relative max or min. So we know we have a relative max or min when the first derivative is 0, but we can now use the second derivative test to tell if it's a maximum or a minimum. If the first derivative test is 0, meaning if we have a max or a min, if the second derivative of that exact same point is negative, then that means it's a max. If the second derivative is positive, then that means it's a minimum. Now that seems like it's backwards, and a lot of people get confused by this, and so let me explain. Again, if the first derivative is 0, and we're trying to tell if it's a maximum or a minimum, if the second derivative is negative, it's a max. If the second derivative is positive, it's a min. Here's why that works. Let's look at the example where it's a maximum. Okay? Our first derivative is 0, and so that means we have a maximum. What's happening right here? For a maximum, that's a place where we're accelerating downwards, like gravity. The gravity is pulling the rock down, and so our second derivative is going from positive. Our first derivative is going from positive to negative, and so that means we're concave down. That's why the second derivative being negative is a maximum. Our rate is itself decreasing. And remember, the second derivative is telling us how the rate of the first derivative is changing. So if our first derivative is falling, that means that we're concave down, which means that the second derivative would be negative, and when that happens, it carves out a max. I know that's a little bit hard to understand, but you'll just have to get used to it with practice. Let's look at the opposite. Let's look at when we have a minimum. What's happening when we have a minimum? Well, in that case, our first derivative is going from negative to positive, which means that we're accelerating in the positive direction, which means that our second derivative would be positive. The second derivative tells us how the first derivative is changing. If the second derivative is going if our first derivative is going like this, then that means we're being carved concave up, which means our second derivative is positive because our first derivative is increasing from negative to positive. So to recap, if our first derivative is 0 and we're trying to tell if something is a max or a min, you can use the second derivative, but just remember that it's the opposite of what you expect. If the second derivative is negative, it's a maximum because we're falling, which makes a maximum. If the second derivative is positive, it's a minimum because our second derivative being positive means it carves out a minimum. That's the second derivative test in a nutshell. In the next video, we'll look at a couple examples so that we can make some sense of this.